5 minutes past 4, and everyone in the waiting room has been admitted. Welcome to what I think is going to possibly be the official last SASQUA seminar series session for this year. I will keep you updated if we do have some more speakers come online for November, but at this stage, it looks like the special edition where we have Frank and Mateng looking back a bit further than Quaternary in terms of the Oligomyosin palaeoenvironments, specifically the palynology work that they've been doing on that. And without further ado, I'm going to stop sharing my overview screen and let Frank take us off with his title of his talk is the Oligocene-Miocene, a period of strong global paleogeographical, climatic and floral shifts, preparing the stage for today's biodiversity. Thanks, Frank.
Okay, hello everyone. I will now share my screen. Okay, I think you should be able to see it now.
Yes.
All right, so what I will do here is basically, I will not only tell you how Oligocene-Miocene period can be seen as a preparation of the stage for today's biodiversity. I will also prepare the stage for Mateng's talk. So I will give you some kind of in the form of a short review, some kind of background information, why we think that the Oligocene, especially the late Oligocene and early Miocene, is a period where you can see very strong changes in the composition of continents, but also when you look at climate and vegetation. So, of course, the starting point for us is to understand and to look at the roots of the current biodiversity in South Africa. So it's always interesting to see that when you compare all nations in the world, then number 3, the bronze medal, goes to South Africa for the 3rd most biologically diverse country in the world, with probably close to 1 million plant and animal species. Of course, the actual number is not known, but 7.5% of all vascular plants worldwide are occurring in Southern Africa, with more than 13,000 endemic plant species. And of course, as we know, the fynbos biome plays a very special role here with more than 9,200 angiosperm species. And what we always want to know is how and when did this plant diversity actually emerge? When we're looking at the current biomap of South Africa, that is after Muchina and Rutherford, of course, the map here, then we can see that there are 9 distinct biomes in South Africa, but we will not talk about all of them. But I will, for certain reasons, now point out how diverse they are, because that makes Mateng's talk maybe even more interesting. Because nowadays, when we look at the Cape, then we have the fynbos biome here, where we normally have an average annual rainfall of more than 300 millimeters. We have poor soils, and we have a largely treeless vegetation, where we have dominance of certain families, especially the Proteaceae, the Proteas. Then we have the heath family, the Ericacea, we have the Restionacea, and there are a number of other families of importance like the Iridiacea and the Bruniacea. And embedded in the fynbos biome, but also in other biomes, we find a completely different type of biome, and that is the so-called Afro-temperate forest. So obviously we have trees here, we have a higher rainfall, and the soils are varying, but we find a completely different composition of taxa than what we find in the fynbos, although they are adjacent to each other. So the Podocarpacea, the yellowwood tree family, plays a huge role, but there are, for example, members of the olive tree family also can be found in that forest. This forest biome is extremely tiny and mostly widespread, or the only larger part can be found here at the southern coast, where my cursor is in the area of Knysna and Tsitsikamma. Then we have the largest biome by far, that's the Savannah biome, which stretches all the way up to Eastern Africa, and it's a grass-dominated ecosystem shown here in orange. With typical are the thorn trees, are the acacias, and then we have also in the summer rainfall region, yeah, here in the east, but along the coast of the Indian Ocean, we have a tropical, subtropical biome called the Indian Ocean Coastal Belt biome, with very tropical trees, for example, Sapotacea and also palms. So nowadays at the Cape, we don't find any palms, but here along the Indian Ocean, that is where we find the palms growing. And there we also have typical forest vegetation units, for example, on a dune forest. So very diverse in every single aspect. So, but if we want to ask for the one unique biome, then we will end up at the fynbos, because the fynbos biome is not only a biome, it's also together with adjacent biomes part or the so-called, it's even a plant kingdom in itself, in its own right, which means that it's has such a unique set of plants that it is even on par with the Palearctic, for example, which is much larger. And so what is also interesting is that we have, of course, Southern Africa surrounded by oceans. And along the western coast, we have the Benguela Current. And with it, the Benguela upwelling system, which is a cold sea current. And that cold sea current actually bringing water from Antarctica, that triggers the relative aridity and also the winter rainfall at the Cape. And so that is often brought into connection with the whole emergence of the fynbos biome itself. So here you can see the observed species richness, and also here remarkable is the fynbos biome. There are other centers of diversity here, for example, in Pondoland or in parts of KwaZulu-Natal, but the fynbos biome is by far the most pronounced ones of those diversity centers. And of course, if you look at the fynbos biome, you might be intrigued by the question, when do the fynbos plants actually evolve and why? And that is summarized here in one diagram. Of course, I mean, in science, you always have a concurrence of different ideas and hypotheses. And this one is a paper by Van Santen and Blinder, 2020. And they oppose two different models here. One is called the Mediterranean climate model. And that Mediterranean climate model is very much built on the idea that the fynbos clades are developing in a winter rainfall climate, and the winter rainfall climate is, as we know, triggered by BUS or by the Benguela upwelling current. And for the Benguela upwelling current, due to several studies along the western shore of South Africa, done, for example, by Lydie Dupont and colleagues, we know relatively well when the Benguela upwelling current started. So that is shown here, this time period, by those two red vertical lines. So it's about 11, 12, 13 million years ago. And so if you would have sort of a strong support for this Mediterranean climate model, you would assume, that is what the authors are, at least are postulating here, that most of the fynbos clades, which are shown here in some prominent examples, would emerge during that time period when BUS first starts. So, and the authors use phylogenetics here and an approach where they also calibrate the phylogenetics by looking at fossil evidence, and then they print Bruniacea, Restonacea, Protea as very prominent fynbos clades here. And as you can see, they emerge much earlier. Yeah, so for example, Bruniacea are known since the late Cretaceous. Restonacea evolve most probably at the end of the Cretaceous. So you can see there is a large arrow margin. And then proteas are known since the early Tertiary, and so on and so on. And only some of them, like Clifortia and most of the Erica Cape Plate, are actually evolving at around a time where you already have bus. So that means they strongly support a second model, which is called the Oligotrophic soil model. And that is built on the idea that since the split up of Gondwana, you have sort of erosion since that time period, and soils are becoming poor in nutrients, which is in fact true for the typical fynbos soil. So they support the idea that the fynbos clades have developed more or less independently from the Benguela upwelling current. So when we look at the paleogeography, there are, of course, global parameters like the opening of the Panama Strait, the already open Drake Passage, the opening of the Farm Strait, and they all point to that you already have ice caps, because the Drake Passage already allows the exchange or circulation of cold waters around Antarctica. But you also have a very strong warm, humid influence, so tropical waters can circulate here in the tropical area because parts of the Tethys are still open and the Panama Strait is open. So the climate is fluctuating. We will mostly look now at the Oligocene, Miocene. As you know, in the Eocene, we still have very high average global temperatures of about 24 degrees. And we can see a strong decrease, especially here in the Oligocene, but also strong fluctuations. They are, of course, bound also to those tectonic events, which I've already introduced you to. And when you look at the end of the Oligocene and the beginning of the Miocene, you can see an especially strong decrease of global temperatures, whereas in the mid-Miocene, we reach another terminal maximum. So very strong fluctuations. When you look at the partial pressure of CO2, you can see an even stronger trend from the Chettian until the Burdigalian in the early Miocene, which is a strong decrease of the CO2 partial pressure in the atmosphere. And that, of course, has an influence on C4, C3 plants, on photosynthetic pathways. But you should always keep one thing in mind. If you have temperature trends, you also have global sea level fluctuations, which is certainly bound to also the way that, for example, ice caps are building up and that the sea level will then drop. And so it's not very surprising that you have a sort of like a parallel pattern when you compare the temperature trends to the sea level fluctuations. Here also very strong fluctuations, a strong drop in sea levels down to about minus 40, minus 30 meters of what you have today. But then during the early Miocene, a strong sea level increase until you even reach here during the early Miocene, a sea level which is about 20, 30 meters higher than today. So very strong sea level fluctuations, which have to be kept in mind when looking especially at coastal plant communities. And this now is a snapshot of about 20 million years ago, given to us, thankfully, by Robert Scotese. And as you can see, around 20 million years ago, the sea level was already higher than today. So a lot of this coastal area in South Africa would be flooded. And that is also shown when you look at reconstructions from the Langebaanweg area, which is where you have the red dot here. When you have only an increase of 5 meters, then you already see a strong change in the coastal topography. So that is today's topography. You can see here the Cape granites building hills here. And when you remove the sediments which are built up since the Oligocene, then it would look like that. If you have a sea level increase of only 5 meters, then you would have strong ingressions here. Yeah, so basically you have an archipelago situation here. And that is where we have Langebaanweg, where you have the white dot. And that is Saldanha Bay at the today's coast of South Africa, where you have the red dot. Yeah, and the blue line here shows the so-called Paleo Berg River, which is probably building up delta sediments in front of the coast already during the Miocene. So obviously seashore levels changes have an influence. And that is just a summary of what I told you about. You can see the global mean temperatures dropping since the late Oligocene and then increasing again in the mid-Miocene. So stomata indexes are, of course, showing an opposite pattern to that. And atmospheric CO2 is also, according to this paper, running more or less parallel to the temperature fluctuations, showing a strong drop since the latest Oligocene and then an increase again towards the mid-Miocene climatic optimum. And with that, you can see a spread of open grasslands since the Oligocene, and then spreading of C4 plants with a decrease of CO2 levels here, especially since the mid-Miocene. So all that can be brought into connection and shows you how interesting the late Oligocene beginning of Miocene actually is. And this again shows you changes in the same time period, late Oligocene until the mid-Miocene. Worldwide trends from forested environments to grasslands. In dark green, forest environments are shown, and here also sites here, for example, from Eastern Africa, where you can see an opening up of the landscape only since the beginning of the mid-Miocene, whereas, for example, North America, you have open grassy environments starting much earlier since the beginning of the Oligocene. And of course, that might have influence also or support a trend from C3 photosynthetic pathways to C4 dominating photosynthetic pathways. So there is a lot of changes happening worldwide since the late Oligocene and beginning of the Miocene. But even when you look at very young papers or very fresh papers like the one published here by Steindorf-Stottir et al. 2021, you can see that mostly from the Miocene, they don't show, unfortunately, late Oligocene environments. You have here reconstructions from the northern hemisphere and very little from the southern hemisphere. And when you look at where you find sites in the southern hemisphere, then South America plays a huge role. Australia plays a relatively large role, whereas in Africa, only very few dots are shown, although the authors could have added some more dots, in my opinion, here. But you can see that they sort of reconstruct deciduous broadleaf forests. So during the Miocene, you obviously had a more subtropical forested environment here. And so that is actually sort of the background for the study which Moteng will now show. And so in summary and conclusion, we want to investigate the roots of the current plant diversity in South Africa. We want to establish a link or test a link between the Benguela upwelling system and the establishment of the winter rainfall fynbos. And then we have to deal with two contrasting models. One is called the Mediterranean climate model, the other one, the oligotrophic soil model. And as you have seen, there are strong changes which make this time period, late Oligocene, early Miocene, very important in climate, but also in sea level and also in CO2 partial pressure. So overall, this period is sort of like characterized by increasing shift from forest to more open environments. But as you have seen, we have a scarcity of Oligocene, Miocene records in South Africa. Yeah, and with that kind of background information, I will give over to Moteng. I don't know, Lynn, if you want to allow questions now, or shall we have them at the end?
We could take a very specific one question now before moving to Moteng. If anyone has any burning questions that they want to ask, now is your time. I'm not seeing anything. So yes, Moteng, if Frank, if you could just stop sharing your screen and then we can kick off with Moteng, who is going to be after that great introduction, giving us some detail about the southwestern coast of South Africa, and looking at palaeoenvironments from the same time period. There we go. Yes.
Okay. Good afternoon, everyone. Can you hear me and can you see my screen?
All good, thank you.
All right. Good afternoon, everyone. So I will take you through the reconstruction of Oligomyosin palaeoenvironments along the southwestern coast of South Africa. This talk is based on my master's research, which was supervised by Dr. Frank Neumann and Professor Marion Bamford. The Cape Flora region along the southwestern coast of South Africa is characterized by highly diverse and endemic vegetation. This vegetation is dominated by fire-prone shrubland of the fynbos biome shown in green on the map. The fynbos vegetation is associated with a Mediterranean type climate with winter rain, with wet winters and dry summers. And this Mediterranean climate affects the vegetation along the southwestern coast, along with the cold Benguela Current. And these vegetation, or the influence of these factors, can be seen along or within the winter rainfall boundary. And paleontological sites within the boundary include Langebaan, shown in black, and Saldanha Bay, Noordhoek, Ronderberg, Arnold Pipe, and the Olifants River area. The aim of the study was to determine the origin of the fynbos biome and the influence of sea level fluctuations at Langebaan. And this was done through the palynological assessment of core BH2, which was extracted from the Elandsfontein Formation, which is outlined, or this area with the red outline. A total number of 104 microfossils were identified from the study, and only a selected number are shown in the following slides. Or the black bar shown on the top images represents a scale of 10 micrometers. The top images were obtained from the study, and the bottom images are the closest living relatives of those shown at the top, and these were obtained from various internet sources. Pollen grains of Podocarpeditis, which were found from this study, can be compared to those of the yellowwood tree. And the yellowwood tree is our national tree, and it still occurs in the southwestern coast region. I've also identified pollen grains of Erysipetus otagoensis, which can be compared to pollen grains of palm trees or Phoenix reclinata, and these are typically found along the southeastern and eastern coast of South Africa. We also have pollen grains of Oleodermpelenitis reticulatus, which can be compared to the pollen grains of wild olive trees, or Olea europea africana. And Oleaceae is characteristic of Mediterranean climates and still grows in the Cape today. We've also found pollen grains of Zonocostitis romaneae, which look similar to pollen grains of Bruguiera gymnorrhiza, which is the black mangrove. And these mangroves are found along the eastern coast of South Africa. And they can also be compared to the pollen grains of Rhizophorum mangle, and this needs further study to determine or to confirm which pollen grains it could be close, or which taxa it could be closely related to. And mangroves are important indicators of brackish water conditions and high sea surface temperatures. We also found pollen grains of Peregrinopolis nigericus, which resembles the pollen grains of Brachystegia. which resembles the pollen grains of Brachystegia or the Miombo tree. And Brachystegia is only found or is found today in Mozambique, Malawi, Tanzania, Zambia, and Zimbabwe. And we've also found pollen grains of Mutesia vitawensis, which resembles pollen grains of the Asteraceae family. And we have an example of Gebera, which belongs to the Asteraceae family. And grass or other terrestrial pollen grains are represented by the grass pollen Graminedetus, which can be compared to the pollen grains of grasses. Also found pollen grains of Milfodia, which can be compared to the pollen grains of Restios or Restinaceae, and Milfodia or Milfodia can be associated with wetland and with both wetland and terrestrial environments. We've also found pollen grains of Spaganaceae pollinatus barungensis, which is a wetland taxa that is similar to the berreed or berreed and Spaganaceae family. And we've also found spores of Lyotriletus maximus, which can be compared to spores of the modern climbing fern or the Lygodiaceae family. And we've also found dinoflagellate cysts of Aptiodinium spiridioides, which is an extinct dinoflagellate, and Spiniferitis mirabilis, which is an extant dinoflagellate. The age of the Langebaanweg deposits was inferred from index fossils of the index fossils belonging to Chiropteridium lobospinosum, Cordospheridium minimum, and Aptiodinium spiridoides, which are all extinct dinoflagellates. We've also determined the age from pollen grains of Mutesia vitawensis and Tubulifloridetus and Tepodica. And these index fossils revealed a late Oligocene age to an early Miocene age, and this age is shown by the black stars up to the purple star. And from this, we can say that the age of the deposits is approximately 27.8 to 20.4 million years old. And these stars represent the ages of the pollen zones, which are defined in the following slides. We've constructed a percentage palynological diagram to determine the percentage and fluctuation trends of the microfossils. The y-axis represents the depth of the core, which is 33.03 meters from the surface downwards, and the x-axis represents percentages of microfossils throughout the core. The microfossils indicated at the top were ecologically grouped according to similar habitats and climatic conditions. And these depths were grouped, So these taxa were grouped according to similar climatic conditions and habitats. And then the pollen zones shown on the right were determined based on prominent vegetation changes across the core profile and are arranged from the oldest at the bottom, which is pollen zone 7, to the youngest at the top. Pollen zones 7 to 6 are dominated by forest trees belonging to Podocarpaceae and Fagaceae, as well as Uliaceae. And there are also, and palms are also quite abundant in these zones. They are also spores of Lyotriletus maximum. And based on these taxa, we can assume that the climatic conditions were humid, and that the paleo environment was a warm subtropical forest, which existed approximately 27.8 to 25 million years ago. pollen zones 5 to 3 are dominated by wetland taxa belonging to Milfodia, Homeopunctatus, or Restionaceae, as well as Spaganaceae pollinatus barangensis belonging to Spaganaceae. We also see high percentages of grasses, as well as palms, some palms. And another interesting thing that we see is the high percentages of Aptodinium spiridoides. And based on the fluctuation of Aptodinium spiridoides, we can assume that there were 3 marine transgressions and regression events. And these can also, and if we look at Aptodinium spiridoides, we can see that the percentages were approximately 60 at the bottom contact of pollen zone 4, and increased to roughly 90%, and then increased again to about 70%. Decreased again to approximately 70%. And based on these fluctuations, we can assume that there were 3 transgression and regression events. And these can also be seen on the global sea level curve shown here, which was recorded, or which was represented in a study by Miller et al. Therefore, we can say that pollen zones 5 to 3 are associated with a high water table and prominent sea level fluctuations. And we can also say that the environment had a shallow marine influence, and that it possibly represents a wetland to savanna woodland, which existed approximately 25 to 23 million years ago. And as I've already mentioned, global sea level rise and fall events were mostly in pollen zone 4. And pollen zones 2 to 1, which are the uppermost pollen zones, are characterized by very low palynomorphs. However, we see that Botryococcus algae and Aptodinium spiridoides, as well as Benferitis mirabilis, are quite high in these zones. And based on the increases of Aptodinium spiridoides and Benferitis mirabilis, we can assume that there was a 4th and final transgression in pollen zone 2. Therefore, we can say that pollen zones 2 to 1 are characterized by a marine transgression event. And based on the low pollen recovery, we can assume that there was reworking in a lagoon environment. And these pollen zones are approximately 22 to 19 million years, or the environment was probably existed 22 to 19 million years ago. And excuse me. Based on these vegetation changes, we can assume that the Southwestern Cape region, which is shown in green on the map, was characterized by a mosaic of subtropical forest elements with fynbos understory, which later transitions to a savanna woodland environment. And this is because we find elements of the fynbos biome, such as Proteaceae, and elements of the Afrotemperate forest, such as the Podocarpaceae, and elements of savanna woodland, or such as Brachystegia. And also we find elements of the Indian Ocean coastal belt, such as the palms. And based on this mosaic vegetation, we can assume that the climate was warm and that the Benguela Current was not yet established. This record shows that the paleo environment at Langebaan was influenced by several factors working together. Marine transgressions imposed brackish water conditions and localized flooding on the environment, leading to the retreat of the subtropical forest. And these transgressions 4 to 1 can be correlated with global sea level transgressions, which were quite high during the deposition of the Elandsfontein Formation. The partial pressure of carbon dioxide was, however, lowered during this time period, and this decrease favored C4 plants, especially grasses, and the expansion of the C4 plants led up to the opening of the landscape, which was seen by the increase of grasses in pollen zone 4. And global temperatures were frequent, or they fluctuated frequently, and had possibly had little impact on the vegetation change in the Langebandberg section. This study affirms the existence of subtropical to tropical forests with an understory of early fynbos vegetation. The presence of mangroves indicates that the climate was warmer and sea surface temperatures were higher than today. And dinoflagellates help us determine the biostratigraphy, or the age of the deposits. And they also show us that there was a strong marine influence on the paleo environment. And the 4 marine regression and transgression events can be correlated with global sea level changes. Therefore, a protofynbos biome was already present during the late Oligocene to early Miocene, prior to the establishment of the Benguela Current. And I'd like to thank my funders, or National Research Foundation, the Center of Excellence in Paleosciences, and the Palaeontological Scientific Trust. Thank you.
Still muted, Lynn. Thank you, sorry. I'll repeat myself. Thank you so much, Moteng and Frank. If you want to put on your video so everyone can see you, we can maybe take some questions from the audience. Really fascinating stuff.
Thank you.
Trevor.
Thanks.
Yeah, afternoon. Thanks, guys. Can I just ask, just listening to the two talks together, Frank, you mentioned that you're looking at a minimum of a 5-meter rise in sea level. And when you show that digital elevation model, you can see how much further the sea would be inland. Now, how can we link that between the pollen record and what you're showing, Frank, whereas you're going to have possibly a narrower band of each of the biomes? If you think about that environment, you're losing quite a lot of that coastal plain, and you're going to be moving into the mountains probably a bit quicker. So those biomes potentially could be, more concertinaed up together. Yeah. So I just thought of, those two. I mean, it's really fascinating to try and link those two together. But I think it is possible. We don't think about it as we see the fynbos today. It could have been in a lot more restricted zone and between the coastal plain and the mountains. And can I just mention the second point is I'm happy with, the mangroves and all the rest of it. The one I struggle with is just the savanna, because you're basing it on brachystegia, or one of the things. And I know brachystegia pollen, we've got a brachystegia site in the northern provinces. So we've got them in Zimbabwe, then also in the northern provinces. So I'm just not sure how far brachystegia pollen moves. And I just worry about linking it all just on brachystegia alone. Those are my 2 points. Thank you.
Okay, I think I can address the first one, but the second one, also Moteng can add a little bit of information. I mean, you might know that there was a study done at Saldanha Bay, and which shows a lot less fluctuations than what Moteng has shown, most probably because it's a shorter time frame. But part of that study was also reconstruction in a 3D block diagram where we actually pointed out that we have to think exactly about what you said, Trevor, that we have actually quite a vivid topography in a very small area, because, I mean, there was no deposition in between the Cape granites yet. Yeah, so there were really like valleys in between. So, for example, Afro-temperate forests might have grown higher up in a little bit higher altitude, and the fynbos might have formed a mosaic, maybe as an understory of the forest, or on poor soils also, because the Cape granites normally can also don't have so rich soils. So, and yeah, you're right. I mean, there is quite a steep hill then, yeah, close to the sides, quite a change in altitude, and so you might find quite a lot of directly next to the rivers, where you might have an estuarine situation. You might have at mangroves, then riparian forests, then where it was more flat, the territory, you might have had a woodland situation. So we really have to reconsider this change in topography during that time period too. And so that's the one point. So indeed, it was looking completely different, and altitude matters here a lot, especially what you told, what you also said, this vanishing coastal plain, yeah, which was mostly gone. And you have seen what happens when you just add 5 meters of sea level. The second question was about Brachystegia. Brachystegia is a very heavy ornamented pollen grain, which is not flying well. So normally you need to have Brachystegia close to the site. We also found other elements which are pointing to a woodland. So you have to be careful calling it savanna maybe, but indeed there are quite prominent members. Acacias are missing completely. We haven't found, never found any acacias. But Brachystegia does appear. There are indications that Cisalpiniaceae are there. So there are some other woodland elements. So it's of course bold to call that savanna, but on the other hand, I mean, those plants are growing in areas where you have certainly not in winter rainfall regions. Yeah. So Brachystegia, for example, is also known from Nigeria. So it has a very wide distribution. But here in South Africa, it's not well distributed. It only appears in I think one site in South Africa. Otherwise, you really have to go to Mozambique and Zimbabwe to see Brachystegias.
Okay. Okay. Thank you.
And just a comment from the chats. Lydia agrees that the Brachystegia pollen does not distribute very well. And then we also have a comment from Abraham. Is it possible that Brachystegia came from further up along the coast, Angola, northern Namibia? This may point to direction of sea currents. Its presence in the record is rather odd.
Yeah, Muteng, maybe you can answer that.
Well, I don't know, but I can't really explain the presence of Brachystegia besides the fact that it grew close to the sites, as Frank already mentioned, because it is, or the pollen grains are quite heavy, and if I think, and as we've also mentioned, that they only grow in the northern, or in the northern regions of the country today. So it would be, I think it would be impossible for the pollen grains to be transported to the site today. So yeah, I don't think it would make sense for it to be transported by the currents. So I'm not quite sure if I answered the question. But I'd also like to add that we've also found other savanna woodland elements in the record. So perhaps.
The reason I was asking is because there's a core of I think it's Angola, and obviously the Miombo is quite prominent. So like you were saying that there's been these marine transgressions and stuff like that. So there are these major rivers that obviously deposit all these grains like through that transport. And so the question is like this one was asking that if those sediment with these pollen grains is deposited into obviously the Western Ocean. And because of these marine transpiration that you talk about, like, because it's now like, because we think the current is going from south to the north, but what if it was going from the north to the south? Then that way, it's likely that you might get these things somehow lingering.
But there is no evidence that the current was flowing from the north to the south. And well, based on the age of the deposits, the current was already going from the south to the north. So I still don't think it would be possible for the, I don't think it would be possible for the pollen grains to be transported by the current.
You even know that, for example, when you are in an area where you know that Miombo is growing, for example, offshore the Limpopo River, you don't find it too often. There are studies by Annelie Ekblom from southern Mozambique where there was definitely Brachystegia growing, and she hasn't found too high numbers of them. So they don't float well. Yeah. For example, conifer pollen can float, yeah, and they can be transported easily. But that is not true for such a heavy ornamented reticulate pollen like Brachystegia. It doesn't show any transport traces also. So, and we know that there is a huge contribution by very local pollen because Moteng also found huge spore pollen there, which are also definitely not transported long distances. So we don't assume that a big part of those pollen was even transported long distances. There is no indication for that. The pollen preservation is brilliant, absolutely marvelous. You would assume that when something is floating for a long time, even if it can float, you can see corrosion, and you can't see that in those pollen grains. Yeah, they're perfectly preserved.
May I add to that?
Absolutely.
Yes. Well, I mapped also Brachystegia along the coast, and it is only very, very specific positions where it's nowadays growing. So the first thing doesn't transport well. The other thing is you can't reverse the Benguela current or the currents in a way because they depend on the temperature gradient over the latitude, so north-south, and they depend on the evolution of the Earth. So that's so basic that you can't have a major reverse Benguela current. What you do have, of course, is very strong along the coast, the countercurrent. But I don't think that can transport long distance Brachystegia pollen from the north.
Vincent, Shane, you've had your hand up for quite a while. Do you want to ask a question?
Yeah, I want to ask 2 or 3 questions, if I may. Hi, Frank. Hi, Martin. Thank you very much. Firstly, I might have missed this, but how do you know that your grasses are C4? Is that something that that you can identify as C4? Forgive me if I missed that.
No, I haven't looked at phytoliths or any other sources to determine whether the grasses are C4 or C3, but there are several studies which were done on fossil teeth that were obtained from the same study sites and and these fossil teeth of giraffids, of mammalian giraffids, and I think there was a study based on mammalian giraffids, and it showed that the giraffids were feeding on C3 grasses. So they conducted a phytolith study on these teeth. So I think based on the fact that they are from the same area, I can assume that they are C4 grasses.
C4 grasses. I mean, there's always a component of C4 grasses, isn't there? Even in the modern day winter rainfall zone. It's just that it's probably C3 dominated if you just looked at the entire biomass of grasses for at least over the establishment of winter rainfall, which brings me on to my next question, which is there a kind of diagnostic species for winter rainfall establishment along the west coast, or is it more of an assemblage, a general sort of picture, or are there a couple species which are, I'm thinking about earlier, for example, which or its precursors, which are, you know, strongly Mediterranean. Obviously, this is warm subtropical forest, but I'm just thinking in terms of more recent timescales, is there a particular sort of species or a couple of them?
Not from my study, I would say no, but we do have these proto-fynbos elements, and the presence of these proto-fynbos elements can or herald to a drier climate. So I could say they represent a Mediterranean climate species. However, we also see these Uliaceae pollen grains, and we can also maybe assume that they represent Mediterranean climate. But yeah, I think that's as far as I can think of. Yeah.
Oh, thank you. Well, it's a wonderful project, and congratulations for all of the work that you've done on it.
Thank you.
I've got a final question, and I think it's for either of you or both, and that is, you know, the middle Miocene and the early Miocene is typically regarded as a kind of middle of the road future analog under future climate change in terms of just the CO2 forcing. Now, there's a lot else going on there, and in a lot of the climate models, which are quite good. They have quite good predictive power and they're quite consistent. There's widespread aridification in southern Africa under 500 or 600 ppm CO2. But in this case, we have along the west coast warm subtropical forests, so that's not arid. So my question is why? Why do the models not reflect it? Is it that maybe the middle Miocene and the early Miocene is not a good analog for future climates, because are there other things going on? I mean, the position of the continents is more or less fixed. The Drake passages open up and so forth. So we have large-scale circulation patterns, which we'd expect broadly to be at play in terms of climate. So yeah, just that general question. Perhaps I could invite you both to speculate on maybe it's not a good analog for future climate, or if it is, maybe the models are wrong and they're under totally different maybe solar parameters, for instance. And if they're wrong, maybe we don't have much to fear. If the west coast becomes a warm subtropical forest in 200, 300 years, that might be fairly pleasant. So yeah.
Yeah, thanks, Vincent. I mean, first of all, we have to understand that also according to Moteng's biostratigraphy, we are not in the mid-Miocene climatic optimum yet. But secondly, well, it's quite obvious it's not it doesn't fit into this idea of aridification. And but again, it shows you that the sea currents play a huge role here. So whenever you have those cold upwelling systems, like you also have just to the west of the Atacama Desert, if they are active, it causes aridification. So obviously the Benguela upwelling current was not active, because we know that because the mangroves were growing there. If you have mangroves, and if you look at that, you even can probably even say that those mangrove pollen which Moteng has found are Brugueria, yeah, which is now growing in KwaZulu-Natal, then you can exclude any cold sea currents. Even you can't even speak about a cool sea current anymore, because the mangroves need high sea surface temperatures. So obviously this is not an analog situation, because I don't think that suddenly when you come closer to the mid-Miocene that changes, because you have seen the Benguela current is actually developing actually at the end of the mid-Miocene only. Yeah, so you see, obviously you can't just take the whole world and say, okay, this is now a mid-Miocene world, and it's like that and that everywhere, and we can use it as a sort of comparison for the current climate. I think this whole idea is a bit too simplified, and that you actually need a lot of local regional studies, and that things like sea level fluctuations and sea currents, that the whole marine system plays such a huge role. That is shown here again. So, and Vincent, you spoke about, for example, what are winter rainfall indicators. So I would say they are not really winter rainfall indicators in this case, because people also have a tendency again to simplify. They say ERICAs, winter rainfall, but ERICAs are widespread in Europe, and not always where you have winter rainfall. They are found in high altitudes. And in high altitudes, you don't automatically have winter rainfall. It just, I mean, this whole idea is also that ERICAs might grow at the Cape because of poor soils. So I think we tend to overinterpret climate. And we are not looking at soils, we are not looking at marine geology and at sea currents. We just say climate, and that's temperature. And that is how simple we would like to have the world. But I think it is not that simple. And obviously, as Trevor has pointed out, even the biomes might have looked completely different to what we see here. So you can't just say, okay, the fynbos biome is larger. There was no fynbos biome. I mean, if you have pines growing there, if you have Sapotacea growing there, you can't say this was a large fynbos biome. And you don't even know if those fynbos elements, how they were growing. Maybe they were growing in small patches on poor soil. Maybe they were even growing under the forest. That's also possible. So Restionacea were obviously rather a marshland element here. So they are clearly showing that they were bound to wet habitats. And so it is a completely non-analog story for me. And I would always be very careful with those great analogs.
Thank you very much for that answer, Frank. Thank you.
So one question from the chat was, what was the maximum sea level rise indicated? Oliver, apologize, he came in a bit late.
I think you mean for the Langebaan-Weg record?
I'm not sure what he means.
Okay, can you please just repeat the question? Yes, please. Can you please elaborate? Okay, what was the maximum sea level rise indicated? I didn't really measure the sea level rise, or I didn't have sea level rise records. However, based on previous studies of the same study sites, we could assume that well, they mentioned that sea levels rose to about 30 meters, and I think this was mentioned in a study by Roberts et al. 2017. I think Frank and co-authors did the study, so maybe he can just add if I'm missing anything. But I think sea levels rose roughly to about 30 meters above modern sea level.
Thanks, Moteng. I mean, the thing is, really, it was not her job to measure sea level fluctuations, and it's a very difficult job because you have to take into consideration neotectonics. So there are studies showing that the Cape region was lifted up in the Neogene. There are studies showing that this was plus minus the same than today, and other studies even say that there might be a sort of like a downward movement. So it is, there are in the current research, there is nothing telling you, for example, during the Oligocene or early Miocene, to which degree was there actually an uplift? Yeah, and when you think about sea level fluctuations, you need to understand that. Yeah, so I find that at the current point very difficult to tell that, but it is obvious that the sea level was higher. And if you look at that, only a minimal sea level increase of 5 meters already means that you get an estuarine situation, which is something where we have quite a clear incidence here. Yeah, because you find high peaks of dinoflagellates, which Moteng has found. Yeah, and for that, obviously, you have to have a marine environment or a shallow marine environment. But if that was 5 or 10 meters higher than today, we have to think about that, and we have to calculate neotectonics and other parameters to have a better idea about that. Yeah, so, but you can see that it was strongly fluctuating. Yeah, so you have transgressions and regressions. And you can see that it can be paralleled when you take Moteng's biostratigraphical model. It can be paralleled quite well to the global sea level fluctuations. Yeah, but to which degree, that's still an open question. We need radiometric dating on those sediments. We need a model to understand how high the sea level actually was. Yeah, and that is still outstanding. And but there are opportunities there. Yeah. So yeah, that's, I think, all what I can say about that topic.
Thanks, Frank. Any other comments from the two of you before we close off, other than just saying thank you so much for a great and fascinating 2 talks? No further comments. Any other last?
Yeah, thanks a lot for listening.
We've recorded.
Thank you.
We'll put that up on the website and tell people who couldn't make it today, so they can also. Are you publishing your masters, Moteng? What's the plan?
I'm currently busy with the corrections, but I hope to publish. my masters.
That would be great.
Thank you.
Yeah, we actually plan to submit a paper. Yeah, so, and which will sort of be a good reflection of Moteng's work.
Yeah, brilliant.
Mm-hmm.
Thanks, everybody. Enjoy your afternoons. Cheers, everyone. Bye.
Thanks, Gemma. Thanks,
Thank you.
everyone.
Bye, Frank. Bye-bye, Moteng. Cheers.
Thanks, Lynn,
Thank
a
you.
lot for hosting us.
Thanks,
Pleasure.
guys. Really enjoyed that.
Bye.
Cheers. Bye.
Bye,
Well done.
everyone.
That was fantastic. Cheers.
Thank you.
Everybody's